Welcome to our second video in our bioacoustics course. Today we're going to learn all about the basics of bat calls. Now you may notice some overlap in the content between the previous course and this one, and that's because we're trying to reinforce some of our core concepts. Anyway, I hope that you enjoy this course and we'll get started. So what are we going to cover today? We're going to look at call features, call types, some measurements and metrics, and also some ultrasonic distractions. So let's get started. How does echolocation work? So we know that the bat emits a pulse, and that sound wave moves through the air until it hits something in its environment. Then the echo will come back to the bat for it to process. So if there's a moth or something like that, the sound wave itself has to hit the moth and then bounce back to the bat's ears. So let's have a look at some of the call features that help them with this echolocation. The shape of a bat call might be constant frequency, or we call this CF, or frequency modulated, call this FM, or a combination of the both. There's also quasi-constant frequency, or QCF, and that's sometimes used to describe near flat FM calls. So let's have a look at each of these. So when we're talking about call shape, we're talking about what the echolocation pulse looks like when it's graphed with frequency against time. So FM calls have this sweep that changes frequency over time. Constant frequency are these perfectly flat frequency over time. Quasi-constant frequency, they're almost flat. They look pretty flat, but they actually do have a slope in them over time. So how do constant frequency calls work? They're a little bit different. That constant frequency sound goes out, and it's designed to detect movement against clutter. So those moth's wings are fluttering, and that results in a changed echolocation signal coming back to the bat. So we talk about the bandwidth of a call. That refers to the total frequency spread from maximum to minimum frequency. So you might see wide bandwidth calls, which are these big long ones, or narrow bandwidth calls, which have a very small change in frequency. Now let's talk about the structure of an echolocation call. We have the body, or the characteristic section. This is the flattest portion of the call. Before that, you have the initial section, and after that, you have a tail. Now you might not necessarily record all of these parts. The body is generally the strongest part, and that's the part you're most likely to record. But if the bat's nice and close to the recorder, you should be able to get all of these elements. Now a CF call has the same parts. It's got the body, which is that constant frequency section. It also has an FM initial section and an FM tail. Now again, it may or may not show these parts or even include these parts in the case of a constant frequency caller. The tail is the end portion of a call, typically FM, which is either up sweeping or down sweeping. So a tail occurs in both frequency modulated and constant frequency calls, but it can be very diagnostic when it's used with FM calls. I'll show you what I mean. So here you have up sweeping tails. So you can see at the end it's got these little up sweeping ticks. And here is a species that has a down sweeping tail. So after the characteristic section, you see this down sweeping tail. It's pointing towards the bottom of the graph. And when this occurs in the same frequency, it can be diagnostic species. Alternation is where characteristic frequency of the pulses alternates between the pulses. In Australia, we see this, it's very typically in Canolobus and Micronomus species, but there are other species all around the world that use alternation. So alternation looks like this. You often will see alternation in both frequency, but also in call intensity. So you can see you've got a strong call and a weak call, strong call, then a weak call. All right, and you can see those changes in frequency between each one. This is obviously a very perfect example that I've selected out. It's not always as neat and as clear cut as this. Harmonics are multiple parallel components of a pulse. They're different frequencies, but they're all divisible by the fundamental or lowest harmonic frequency. So here we can see harmonics. All right, we've got our first harmonic. This is the fundamental, the lowest frequency harmonic. Then we've got our second harmonic. And in this species, the second harmonic is the dominant one. This is the one that it puts all of the power into. Then you've got third, fourth, sometimes you can even get more. So sometimes species will use the second harmonic as their dominant harmonic, and other species will use the fundamental harmonic as their dominant harmonic. So harmonics can be diagnostic of both family and species in some cases. Let's talk about different call types. So there are different bat call types that we recognize, including search phase, feeding buzzes, and social calls. So search phase is when the bat is flying through the air and it's not necessarily targeting any specific thing. It might just be navigating or searching for prey. It's using a search call. Now, the approach phase is when it finds a target. That target might be a juicy moth, it might be another bat of interest, it might be something new in its environment, a tree fallen down or a big wind farm turbine that's just been put up. And when it does the approach phase, it typically narrows in on the target and the calls become steeper, wider bandwidth, and higher frequency. When it moves into the feeding buzz, this is when it's actually trying to catch a prey item. It's very quiet, they're very frequent, so the calls are so close together it actually sounds to our ears like one sound. And they're really often very narrow bandwidth, quiet and higher frequency. Lower frequency. There can be 1 or 2 steps in a feeding buzz, and that's what I mean by higher frequency. So there can be one higher frequency part of the buzz and then one lower frequency part of the buzz, or it might just be one buzz. So this is what it looks like in a real echolocation call. You've got your search phase, and right about here, it's found something. You can see it starts to get a wider bandwidth on these calls and they start getting a bit more frequent. And as it starts to get quieter, it's closing in on its prey. And then you've got here, this is an example of a 2-step feeding buzz. So you've got your higher frequency calls, then your lower frequency in step 2. Extremely quiet, and to our ears, this will all sound like one sound. Now, why is it important to understand approach phase and feeding buzz and search phase? Well, when you get a nice long sequence recorded on your detector, it's going to be obvious when it's changing phases, but more often than not, you might just record a handful of pulses, so you don't really have context about what the bat's doing in that instance. I've got 2 examples here. We've got Canolobus gouldii and Ozymops wrightii. You can see their search phase calls are here and here. Now, Ozymops wrightii have a QCF type call and Goulds have this FM typical call. So when they're just doing search phase echolocation, the 2 species are very easy to distinguish. But When you've got Aussie mops doing a approach phase call, it can look extremely similar to the Callinolobus gouldi call. This is why it's really important to set up your detector properly to ensure that you get full long echolocation passes so you can get this kind of context when you're IDing. So let's talk very briefly about social calls. We categorize them as social when they're not typical of a species diagnostic echolocation call, and they contain social information. You record them a lot around roosts and a lot around breeding seasons. Now, in some places, social calls can actually be diagnostic of species, but by and large, in a global sense, we don't really have a good grasp on what social calls look like for each species. It is important to recognize, though, that social calls aren't the only way that bats communicate with each other. So there are social components actually encoded into their typical echolocation as well. But these ones are not echolocation. They are purely a bat calling out to his little bud. So let's talk about call measurements. So in Insight currently, we're using zero crossing metrics. So it's actually looking at the zero crossing dots. Now, characteristic frequency, or FC, is one of the most common metrics you'll see in literature. It's the frequency at the right-hand side of the body of the call. So you look at the flattest portion of the call, and then it's the very last dot on the right-hand side, and it's in kilohertz. And often when you hear about someone saying, oh, that's a 42 kilohertz bat or a 28 kilohertz bat, they're referring to the characteristic frequency of that call. Then we've got the characteristic slope, which is the angle of the flattest portion. So it might be a very flat slope or a very steep slope, depending on the species or the call type. And that's measured in octaves per second. Frequency of the knee. This is the frequency immediately before the characteristic section. And this can be really helpful in diagnosing some species. Duration, that's exactly what it sounds like. How long is the call over time in milliseconds? Time between call starts, or TBCS. It's really important to note that this is from the start of one call until the start of the next one. So it includes the time of this pulse. It's also important to note that this measurement can be really thrown off by echoes and other noise. So it's really important to reduce your echoes, or have a look if there are echoes, and really take this measurement with a grain of salt if it does contain echoes. Then we've got our initial slope. Now, I mentioned this one in particular for two reasons. One, it was used a lot in early call guides, and it's the slope of the first 5 points in a pulse, measured in octaves per second. The second reason I mention it is because it can be a highly unreliable metric. And we know that now. Our science and understanding has advanced over time. And if you're getting poor quality recordings, this initial slope measurement is going to be pretty dodgy. So it's definitely one to take with a grain of salt, the initial slope. So let's talk about ultrasonic distractions, and there is a lot of them. So here's a couple of examples. This is often one you'll see in your recordings, and this is a nice zero crossing one. I actually found this one in the wild, a little smiley face. But the most common frustrating factor when you're analysing bat calls is insects versus bat calls. Sometimes it's really obvious that it's insects, and other times they can look a lot like bat calls. And the best way to distinguish insect calls from bat calls is to change your viewing settings. So try switching it to true time. Take out the show the gaps between the pulses, and also zoom out and look at the general pattern of the calls. And over time, you will start to see the difference between them. Then echoes. Now, I mentioned this before. You can see here, this is a file where there's really strong echoes. So you've got the first pulse and then it's echo. The first pulse, then it's echo. So in compressed mode, you might not necessarily notice it if you've got an untrained eye. They'll just look like a whole series of pulses. But in true time, where it's showing the gaps between the pulses, you can see there's one pulse, then immediately another one, then a normal sized gap, pulse, then it's echo. So it's definitely something to keep in mind when you're looking at your recordings. So that's it. That's all we have for our Basics of Bat Call workshop today. If you have any questions, you can always email us at insight@titley-scientific.com or check out our website. We've got a bunch of resources on there.